Herkese merhaba, hoş geldiniz. Bugün yeni bir Nano Open'la karşınızdayız. Bugün sunumunu yapacak olan hocamız Mersin Üniversitesi'nden Doçent Doktor Rükan Genç Altürk. Kendisine veriyorum sözü. Hocam hoş geldiniz. Etkinliğimize katıldığınız için teşekkür ediyoruz. Buyurun hocam. İngilizce de devam edebilirsiniz. Nasıl rahat anlatmayı uygun görürseniz o şekilde. Buyurun hocam.
Katılımcılara bakalım ona göre. Yabancı katılımcımız var mı? Görüyor musunuz? Benim
Var
için
hocam,
fark
evet.
etmez çünkü. Öyle mi? O zaman İngilizce devam ediyoruz. Good morning everyone. Almost good afternoon. Thank you very much for being here. I'm really excited to see many people here in the morning of Wednesday. So I am Rükan Genç Altürk, Associate Professor in Chemical Engineering Department of Mersin University. So I'm going to explain, or I'm going to share some tools that we may use in the design of functional nanomaterials. So I call it Nano Design. I'm trying to introduce you a new term in the manner of nanomaterial design. So let me go with the slides right now. So let me first introduce myself from the beginning to now, because I'm seeing that most of you are students and there are some very important colleagues that are now listening to me. So I made my bachelor degree in bioengineering in Ege University from 2000 to 2005. Then I moved to Spain for my master's studies. Then I continued my PhD there in Chemical and Process Engineering Department of Virgili. There I was working in a biosensor group where I was the one who was preparing the platforms, nanomaterial-based platforms for biosensing. Then, of course, I add some other topics to my studies. Then I turned to Turkey, to my country, in 2011, once I finished my PhD, and started my postdoc studies in Bilkent University in National Nanomaterials Center. After working 2.5 years there, I moved to METÜ, which we know that as it's in Turkish it is ODTÜ, in chemistry department. After finishing my studies in METÜ, I continue my career as a faculty member in chemical engineering department of Mersin University, and from there to now, I'm now working as associate professor there. So my research topic is, as you can understand from the topic, is nanomaterial science, and I may call myself nanomaterials or nano designer. So nano design is the topic that, let me first, I'm sorry that I'm seeing all the, okay, let me go there, okay, better. So I will talk about a topic a term which is the combination of two terms actually, nanomaterial and design, made in nano design. So you may know already what is design, but if you check it in the Wikipedia, so I guess I have okay. The design, when you basically check it in the Wikipedia, is a plan or specification for the construction of an object or a system. So our object or a system here is the nanomaterial, and the result of a plan. So you need to have a plan and specification in the form of a prototype, which in turn becomes a product. So by means of that, the design is there. And when you combine it with the nanomaterial, so I believe most of you know what is a nanomaterial, but European Commission gives a definition for that. It is a natural, incidental, or manufactured material containing particles, where those particles could be in unbound state, or an aggregate, or even an agglomerate, where here our limits are concluded as the 50% of those particles or materials that you have in a number should be in nanosize. So what we mean with the nanosize, the European Commission made a tight limit for that the external dimension of those nanomaterials should be between 1 to 100 nanometer. Okay, this is the definition by European Commission, but when you check the literature, that you will see that below 300 is acceptable mostly for calling something a nanomaterial. In some cases, if the nanomaterial is applied to industrial applications, like for the material science, actually, submicron, like believe the 1000 nanometer, is sometimes accepted as nano. It depends, but the European Commission define it that way. So when you combine the nanomaterial with the design, the term nano design becomes on the hand. So I want to talk about something about the design. So my brother is an industrial designer. He is now making his PhD in Koç University, and also he has his small firm on the computer and design interface for working on that one. So I always saw his work when he was publishing or when we go together with a conference, that they have a way of design thinking. So when they are designing, they don't directly start to draw and everything, but they have a path which takes them through this design thinking to design product. So this is the microcycle that they are following: understand, observe, define the point, ideate, prototype, and test. So first you need to understand, then you need to observe what you understand, then you need to take all the points that you have on your hands to make the product happen. As you see here, it is not a whole path, a linear path, but sometimes it turns around and you have some control points. So this is a work from him when he and his colleagues were designing a product. So this is the first thing that they start. You see that it is like a loop at itself. So this is another another photo that we took when they are working on to make their state of mind. And another one is this one, and what they call is design thinking. So they are forming everything. So I changed that figure into nanomaterial science. So how I can apply this design thinking to nano design. So mainly the talk is going to be about that one. So I changed the little bit in the path, understand the problem, define the right properties, choose the nanomaterial from the portfolio, and synthesize the nanomaterials, choose the strategies to functionalize the nanomaterial, and test the nanomaterial. Okay, so this is the way, the path for the nano design. So for that, what you can do is that you start with the application, or sometimes you start with the nanomaterial that you have. So once you know the application and understand the problem where you are missing in the application, through that you may need to check or define what are the properties that needed for the nanomaterial that you have. Even you can think about if you really need a nanomaterial, or you may use something microstructure or directly bulk in order to solve this one. So nanomaterial may not be the solution to your application. So let's check these ones. So this is again for assembling these paths. So I use logos. So this is my nephew, Mert. He is really interested in the logo making, and he's a genius about logos, and he wants to be logo engineer. I didn't know about a job like that, but still he's 8 and he's looking for a job opportunity, and he's asking to me if there is a possibility for an 8-year-old guy for making being a logo engineer or somehow another way. So what he does, this is the photo that I took when I was watching him doing these giant logos. So he has a bulk of everything. So he has many different parts of logos, and he starts to make small ones in order to see the whole picture. Then he collects everything together, makes a functional one, and finally he gets this tower from these bulk of things. So what we have here actually is the same, because when I say to you, understand the problem, understand the application, you have to know that there are thousands of applications right now on the market that you can apply nanomaterials. So what are those applications? When I ask the students what might be the application of nanoparticles, or if you check the literature, mainly this 8 is in the middle. So you may use nanoparticles for renewable energy, biomedical science, healthcare, food agriculture, or industrial applications, or microelectronics. So this is the basic core of the nanomaterial science and its applications. But then they goes to some small branches, like in renewable energy, you have lithium-ion batteries or electrodes, hydrogen production, and on the other side, imaging, drug delivery, cancer therapy. When you check out the industrial one, nanopigments, refractive index engineering, superplastics, and it goes like that. So yeah, these might be huge, but at the same time, this shows that there is a huge opportunity there for both nanoscientists and the industry, or you as a young, some of you as a young students there. So once you understand the application, let's say that you start with the textile. So you have a colleague who work on textiles and try to add new properties on the textile, and you are the nanoscientist who try to have some connection with the colleague and try to have a new product. So you need to understand first, what are the needs of this textile industry? What are the odds and what are the how to say controversial things in the technology? So you have to first have a huge literature search if you don't have a nanoparticle on your hand. So then the second phase is finding the right characteristic of the nanomaterial. So what are those characteristics? These are again the basic one I am showing. They are more than 20 different property that might be changed by adding nanomaterials to another material. So you are seeing that you may know that nanoparticles, due to their size and shape, because of the quantum effect, they might change the optical properties. Here we are seeing a pure gold and silver, which is yellow or white or shiny, silver shiny. When you turn it to nano size, they turn to, you can obtain from red to green, red to yellow, many different colors, because nanoparticle size is below 100 nanometers. Also, you are seeing here a semiconductive cadmium selenium quantum dots, where you see that the small size of it gives a blue fluorescence emission, while when it gets a little bit larger to 5.5 nanometers, the color is becoming red. So the same happens for quantum dots. The energy band of the bulk material changes when you have the quantum dots. So the band gap changes depending on the size, and you have different electronic properties depending on the size of the particle. Meanwhile, you may have some magnetic property, while iron oxide as a bulk material is ferromagnetic. Ferromagnetic means that, like normal the magnets, if there is the magnetic property is present there, even if you have a magnetic field or not, the material is magnetic. But when you size down to nanometers, to 20 nanometers, the iron oxide nanomaterials become super paramagnetic, which means that they have a magnetic memory. What does it mean? The magnetic memory, the material is magnetic only when there is a magnetic field. So when you take out the field, the memory goes, so the material becomes non-magnetic. So we call this super paramagnetism, and it is used in drug delivery systems, MRI imaging systems, and in catalysis for separation and for some degradation studies. So there are many different properties you may have with different combination of nanomaterials. So what happens when you try to choose it. So let's say that you choose and you need an optical material, okay, which may need a magnetic property at the same time, depending on the application that you have, but also it needs to be non-toxic. It needs to be surface modifiable. So you may need to modify the surface afterwards. So which nanomaterial you are going to use? The one that you had already on your hand, this is a possibility. Or you may have the risk and find a new material. For that, you have to read thousands of articles. Or basically, you can go to read some very good reviews that a little bit classify the nanomaterials of the state-of-the-art material. So this is some ways of classification of nanomaterials from some reviewers, but mostly you see this simple. So it's like depending on the composition, they might be metallic, biometallic, metal oxide, or depending on the functionalization, they can be organosilans, polymers, surfactants, and so on. But this is a very simple one. These, the end, are more realistic, and you can increase that one. So what does it mean? It means that you have a huge opportunity and huge design capacity there, that depending on your abilities to find the correct answers, you may design 1,000 different ways and 1,000 different nanoparticles for different applications. This is a huge opportunity, I believe. So there are some, this is the basic, okay? There are some methods for nanomaterial science. There are the chemical synthesis ones, physical methods, and biological methods. And when you follow these basic ones, once you choose the nanomaterial that you want, let's say that you want to prepare gold nanoparticles, there is a Turkevich method where you can simply have gold nanomaterials of different size. So from bottom up or from top down, you can choose the methods. What you will have in the case of nanomaterial is first generation nanomaterial. What do I mean with the first generation nanomaterial? Is that it is the nanotechnology that we are already in. Almost for the last 20 years, we are using first generation nanomaterials. So it is the one that you have pure nanomaterial, or sometimes you have a coating on it, okay, for protection or for silencing some biological activity or so on. So what you have from this very first part of the step will be the first generation nanomaterials. If we try to explain it with the Lego, this is the Lego of the first generation. So you have very simple structures that on your hand. So if you want to go further and functionalize it, you are going to second generation nanomaterials that not only you have the core, that this is the one that we are right now moving around. We passed a little bit the first generation nanomaterials. Now we are in the second generation nanomaterials, that you may add some biological activity, you may add some chemical activity, you can have two different nanoparticles together in a core shell material for making the second generation materials with a functionality. So I can call this second generation Lego, where you have now shape, structure a little bit better, that everything is almost there. So if you want to go further, if you want to go for more advanced studies, it is the one we call third generation, where robots, nanorobots, and nanomachines are coming. So not only you have the functionality of the nanomaterial, but those nanomaterial may behave themselves, may move themselves, and may have some real roles in the industry or in biological applications or so on. So these nanorobots that we are going to, we haven't yet reached yet there, but we start to enter that era, the third generation nanomaterial era. So this is the one that we are now going, and we are having all the materials that we have that's for designing those nanorobots for future applications. So I can call this Lego of the today's generation that is not yet, we are not yet there, but we started to have those nanorobots. There are some couple of literature on those nanorobots. So by this way, I would like to also congratulate Hamilton for the Grand Prix, for winning the Grand Prix also. So let's turn back to design thinking to nano design. So I will give you some examples of how we can use these paths for second generation and first generation. Some of those samples I'm going to show you are going to be first and second generation nanomaterial design. So I choose, I guess, 3 or 4 applications on my mind, and let's go how we can solve those problems with nanomaterials. So this is an article from my PhD. I really like it because it is almost my first in the area. So it is on signal enhancing thermosensitive liposomes for immunosensor development. So I believe you know what is sensors. Sensors are tools for detecting and analyze. It can be a gas, a liquid, or a probe, any probe for some disease detection. So immunosensor means that you are using the immuno tools for development of the sensor. So what are those? Antibodies, anticorps, for sensing the analytes. So in this article, we were trying to develop an immunosensor for carcinoembryogenic antigen. What is carcinoembryogenic antigen? It is a probe for post-op follow-up cancer therapy. So for mammalian, I guess for colon cancer, for many different cancer types, CA molecule increases in the blood. The blood levels increases to 1,000 or 2,000 levels, while normal people have a level of 2.5 nanograms per milliliter. But it depends on if you're pregnant or a smoker, these levels can increase. So if you have, here you are seeing that the patient has before the chemotherapy, patient has 715 nanograms per milliliter on the blood of CA. Then he got the treatment. After the treatment, the level turns to 4.6, the measured level. From there on, mostly the physicists are following those levels from the blood, monthly or 6 months away, that they are checking if the levels are increasing back or not. If it increases, it means that the tumor turned back and you have the cancer, your cancer is back. If it goes with these steady conditions, it means that it is not repeating back. Okay, it is for post-following of the patient. So the level may change from people to people, and it may depend of the age of the patient. So since you see here, we are going below the 4.5 nanograms per milliliter, and if the sample has some problems, or if you don't have enough sample, you may not measure those levels. So what we were thinking that we want to increase the sensitivity of those immunosensors by adding some moiety to increase the signal, okay, the immunosensor signal. What do I mean with the signal? This is an traditional immunosensor. So in this traditional immunosensor, you have an antibody on the surface, which is attractive to the analyte. Okay, so it can, there is an affinity to this antigen, and antigen can bound to the antibody. So you have in the normal immunosensor, you have a secondary antibody with an enzyme, and this enzyme can produce electrochemical signal. So one analyte for one enzyme means that you have one signal. So it means that if you have a nanogram of analyte, you will have a proportional signal from there. So if you have a moiety to increase this signal, you need to have several enzymes for one analyte. So how you can do that? You can encapsulate the enzymes in one nanocarrier. By this way, you can increase the signal from 1 to 10 or 1,000. So for that, we use liposomes. Liposomes are lipidic materials where they have a hydrophilic core in the inner side, and they have a surface which can be modifiable with other materials. So I designed a liposome for this purpose, which can encapsulate many enzymes at once. And also I designed a surface for them, which enable the attachment of the antibody from right parts, that it can also see the antigen and can attach with it. So the problem with that, what is the design problem here? That liposomes can be normally in the traditional way can open with the detergents. Okay, they are using detergents to open up the liposomes. But what happens when you use the liposomes? Back then in 2010, there were very few studies that used liposomes as signal enhancer. So the design wasn't finished yet. So these detergents, surfactants are attached to this surface, and they interfere with the signal. So when they interfere with the signal, instead of getting this tiny background, you may have a background from here. So your signal is diminished by the background signal. So use of detergents were not acceptable for immunosensors. So I had to find a way to open up these liposomes. How can I do that? I checked the biology. So in biology, liposomes assemble membranes, lipid membrane of the cell. So lipid membrane of the cell can be opened with the external stimuli like electrocharge and so on, or ionic strength, change in ionic strength, pH, temperature, or some with use of some ions going in and out, or sonic ways. So from those, I had to choose one, and I will choose the temperature because I may design a liposome membrane where when you heat the system in a mild condition, of course, that is below the Tmax of the enzyme, that I can open up the liposome, the HRP goes out, and I got the signal. So I did all my design through that idea, and I designed the liposomes. I changed their surface with the antibody, and by this way, I got 11 times higher signal than single HRP. So what does it mean? If normal immunosensor gets the limit of detection, the lowest limit that's get is, let's say 5 nanograms, what I did get is 10 times lower than that one. So I could detect 10 times lower than the ones that is done by traditional way. So this is one solution. I solved three things in one, we solved three things in one design. We increase the signal, we effectively bioconjugate, and we get rid of the background signal. So another one is came from a company, Bionorm, in Izmir. So we designed a smart nanocapsule for pancreatic cancer treatment. You know that sadly, it is very sad that pancreatic cancer is one of the worst cancer types in the world, where the survival for 5 years is only 10% right now. It increased from 4% to 10 in the last 10 years. And the problem with the pancreatic cancer is that it's caught too late, and effective treatments for this prolonging the life is not present yet for the ones who is already going on. So the way that treat pancreatic cancer or try to treat pancreatic cancer is gemcitabine. So this is used in the clinically used and with combination of different drugs, but it is not effective yet. So there are some other clinical trials going on for treating pancreatic ductal adenocarcinoma. So oleandrin, maybe you have seen this one in Mediterranean sites. All the rows has this one for this flower. We call it Nerium oleander. This is the biological name. So Nerium oleander is tropical one, and it is a material inside which calls oleandrin, is known as a therapeutic molecule, which can be effective in many different cancer types. So in this case, oleandrin molecule has been used for decades for cardiac treatments, some cardiological treatment, because it's a cardiac glycoside. So this oleandrin has a possibility to also treat pancreatic cancer patients, because there is a phase 2 study going on right now that shows that it is on it is on a cold extract of the Nerium oleander leaves. This is a direct extract, not the pure oleandrin, and it is now in phase 2 studies for the last 5 years. And it, I guess last year there was a report on it that it has a potential to treat some types of the pancreatic cancer. So from there, Bionorm, Bionorm and our colleagues in Izmir High Technology Institute ask us for if we can find a nanocarrier for that, because oleander is a toxic molecule. It is not toxic only to tumor cells, but it is toxic to the healthy cells, especially heart cell. Okay, so it may result in heart attack. So in order to increase the bioavailability of the oleandrin to pancreatic cells, it should be covered with something, and by this way prolong the way it goes to until it goes to the cancer tumor cell. So if we check the material, you cannot add any molecule with a simple chemistry for targeting you can not add an anticore to this one because the chemistry doesn't help us. It is very difficult to modify the molecules. So they ask us if we can find a smart nanocarrier for this one, and also it would carry a targeting moiety. So when I was in my PhD, I had a colleague called Elena Vaj. She was working on cyclodextrin-based nanomaterials. So since we are all in biosensing group, she was doing it for biosensing applications. So what she was doing is that she has a gold core in the middle, and she was adding cyclodextrin-based polymeric structures on and on onto this gold nanoparticle, and they made a core shell hollow nano vesicles. So how they make it hollow? They melt the gold inside with acidic application, and it results in hollow nanovesicles by this way. The trick in here that they add azobenzene, and using azobenzene photoisomerization, which means that when you add heat or UV light, when you direct UV light to these molecules, they change their structure, and by this way the pores are open on this carrier, and it release its cargo from inside to outside. So they were using it for sensors. I said why I'm not using it for the drug delivery system, but there was a problem, because UV light cannot be used for deep tissue treatments. It is just for on the surface. Okay, you can only treat the surface of your tissue. So I need to change something. So what we change in here is that from another very brilliant article, we have seen azobenzene-based rotaxane. So rotaxane is most likely work the same ways, and but instead of UV light, it works with near IR, and in near IR conditions, it turns from cis to trans form, and by this way, they made a system that open up. So we propose the project on this one. Instead of using azobenzene, we will combine it with rotaxane in here, and we'll form a material that can open up. So for that, we have some more from Inicio and from ITE again, Professor Dr. Devrim Pesanokvor. We are now trying to combine this light-responsive polymeric oleandrin with another design, microfluidic-based 3D cell culture design, and try to prove our concept before going to in vivo studies. So we are now on the way that we are going to have the nanocarrier, and we will try the efficacy in these microfluidic systems. So I'm really proud of this work, and I hope we will get very good results for future. So let me see the timing. Okay, very good. We have still time, I guess. So now, till now, I explain you polymeric and lipidic soft nanomaterials. Now I'm going to organic or inorganic nanomaterials and their design. So in our lab, we have both ways. So, but our for the last, I guess, 5 years, we concentrated on really fantastic nanomaterial, which we call it carbon quantum dots. But coming from there, I would like to first show you the literature about that. Heavy metal-based quantum dots I showed you. They are those quantum dots can be optic properties or quantum dots can be changed by changing their size. So not only by changing their size, but the Kershal formulation can be also changed. By this way, you can have different colors and different color nanoparticles with different electric properties. So the electrochemistry of the material is also affected by the size and the formulation. But the problem with, you see that the global quantum dot market size in 2020 reached the millions, okay, $1 million. So you see that from 2013 to 2020, the market grows 30%. So where they are using them, these quantum dot display devices, you may see the OLEDs, so laser devices, photovoltaic devices, sensors, light emitting devices, anything anywhere. But the problem with them that they are based on heavy metals. Not only the material that they are done, but also the solvents that are used for synthesis of these quantum dots are toxic. So since the market is growing, it means that the environmental results will be also in the future affected by those toxicity that gets, and they are expensive. So there should be a greener way that can maybe, not all, but can change a little bit the weight from heavy metals to the greener solutions. So what it could be, in 2014, when I was reading an article, when I was checking for the literature, I have seen this article. Biomedical breakthrough, the main carbon nanoparticles you can make at home. It is fantastic. So I read the article, and the article says that if you have a microwave, or I'm saying if you have any kind of oven, if you have honey, molasses, I think you know molasses, it is pekmez in Turkish. If you have honey or molasses, or you have anything to cook, doesn't matter if it should be only the organic material, it should need to have carbon inside. You just mix them together and cook it for a few minutes until it's caramelized, you will have nanoparticles with high luminescence. So you can try it at home. When our families are preparing pigments, they form also some ways of carbon nanodots. So why they call this carbon nanodots? Because they are fluorescence. So carbon is black, you know. Now carbon nanotube is black, graphene is black. Although there are some now clues that some carbon nanotubes and graphene also may give some fluorescence. But they are so new studies. But in 2004, carbon nanodots found by mistake. So they were trying to make purified single wall nanotubes. When they are trying, they have found that 1 fraction of this whole product is fluorescence. So when they go through that, they have found that this is the carbon dots are carbon-based nanomaterials, which where they have amorphous or zero dimensional or spherical structure, and they might be single layer or multiple layers, and they are fluorescent some way. Till now, the physics beyond this fluorescence emission is not understood yet. Okay, still physicists are working on to understand why this fluorescence happening. So you see that they made carbon nanoparticle synthesis from candlelight. They made by laser ablation. Another one made some from graphene. Another is from graphite, and so it goes on until 2014. The researcher find that you can do it from any carbon source. So what I mean any carbon source is this one. You can use any waste to make this natural carbon source. I am making it simple, but you will see how we also move there. So the first one that we did was fluorescence. We were thinking that it is fluorescence, but the fluorescence was so poor when we now compare it after 7 years. So these are how you can do them. There are some top-down and bottom-up procedures, like laser ablation, sonication, chemical oxidation, and arc discharge. By it is top-down means that you have the bulk, and using these methods, you crack this bulk into small size nanomaterials. Bottom-up means chemistry. So thermal carbonization, hydrothermal system, microwave, acidic treatment is bottom-up. So you are using chemistry for collecting from from atoms, molecules to the material itself. So from there, they have been used in bioimaging, LEDs, solar cell sensors, and nowadays in many different applications. So this one was our first attempts, you see, and these are the one that now we can do. We can have different colors. Back then in 2014, there were only blue one. Not only for us, but for most of the researchers, there was no other color but blue. But then researchers find out that depending on the size, crystal structure, especially doping, if you change the surface properties by doping with amine groups, by doping with carboxylate or sulfur groups, or if you add new metals onto the surface, you may change the color of the carbon dots. You see that there is no difference than the colors, and are no different than the semiconductive quantum dots from heavy metals, and quantum yield of them are already reached to the same level. So where you can use carbon dots, the very first we used in different, the very first articles that we have was on the production, on the synthesis, because nobody knew the carbon dots back then. So we were focused on to have different colors, to have different conductivity, to have different size. But then once we understand the material, we start to go with the applications. So the very first applications that we have for the carbon dots was the supercapacitors. Since they are electrically active because they are done by the carbon, why not we exchange the carbon material in the supercapacitor with the carbon nanomaterial that we have? So a supercapacitor is basically, I'm not a physicist, but it's electrically known as the electrochemical capacitor because it stores electrical charge in the electrical double layer of a surface electrode interface. So basically, it is very simple equipment where you have two electrodes, one separator, and you have electrolyte in between. And by this way, the electrolyte is moving from these electrons are moving in this surface electrode interface. So this is the commercial supercapacitor electrode surface. You see that it is not homogeneous, it is bulk carbon on the surface. What affects the performance? Surface area, pore size distribution, shape, accessibility, electrode, and electrical conductivity. Team from our partners, that's Professor Dr. Emre Erdem and Kasım Hocakoğlu. Emre Erdem, you may know, he is the faculty of Sabancı University, and Kasım Hocakoğlu is from Tarsus University. So when we have a talk about carbon dust and application to supercapacitors, we first think of that so the different color means that they have different defect centers. So how these defect centers affect the capacitive behavior? So we made multicolored fluorescent carbon dust from the gas cola drink. So why we use the gas cola drink? Because it has high amount of sugar inside and high amount of carbonous material. So by using different methods, we had 3 different colors, and we apply this material on manganese electrode. Manganese is a good electrode for capacitors, but the point that it is not conductive and that it has issues with the porosity. So increase the porosity of it and add some conductivity. We covered manganese electrode with carbon dots, and on the other side we use reduced graphene as a second electrode. And by this way, we achieve really high voltage, really high photocapacitive efficiency with 70.3 microfarads per centimeter square. So this was very great work. We start with that and we continue, of course. So then, for the first time, we use carbon dust as a real electrode. One is combined with the polymer, a conductive polymer. We combine carbon dots with on the first layer combined with the carbon dots to increase the properties of polyaniline, which is again a polymer used for the supercapacitor applications. But again, it has some problems with the porosity. It has some problems with the homogeneity of the electrode and so on. So to diminish this, we use carbon dust as a filler to fill the material for increasing the ion exchange there. We made these very nice supercapacitors. One side is painted together carbon dust, the other side is only carbon dust. So this study was the first one that we used the carbon dust as an electrode in supercapacitors. We got huge efficiency with that. We got a specific capacitance of 595 farad per gram. So this was huge outcome. Now we are continuing with these studies to have smart space capacitor with the Dr. Erdem. So of course we didn't stop with there, because we have seen that we can use them as an electrode. So we proposed with Dr. Emre Gür from Atatürk University another study that these colorful nanoparticles are used in solar energy. So it is obvious that these optic properties of quantum dots are assembling with, you can reassemble with the organic carbon quantum dots for lowering the series resistance in perovskite cells, for fast charge transport in a photovoltaic cell, or pore filling by manipulating the gaps between. So we did this one in supercapacitor, and we said why we cannot do it in perovskite cells. So we made these colorful thin films and apply it in the electron transfer layer of the perovskite solar cells. You see that we had 4 different colors. We have several in here, but the 4 was chosen because of their capacity, because of their increased conductivity. And we got 8.2. It is not that high because in perovskite cells now they reach almost 20, but for this assembly, it is quite good because we had 32.26 increment in the efficiency when you compare with the reference. This was a huge outcome, and I guess we are going to have more studies on that one. So, okay, I'm going to finish soon with this one. So I will just give 5 more minutes for explaining one more study, that antimicrobial and anti-allergic systems. So you know licorice mayan in Turkish. So it is an antimicrobial material. So friends from a textile industry ask us if we can have anti-allergic or antimicrobial studies. So we made fluorescence carbon dose from mayan roots, and with our colleagues, we have shown that they are antimicrobial and anti-allergic. We show it with the in vitro studies. And here there are some images showing the textile with carbon dose, and there are no bacteria around the textile and below the textile. So this is the same image of the textile where there is no carbon dot. The bacteria has grown. Here also the bacteria has grown, but in the textile that we have carbon dust, there is no bacteria on the surface. So this was very good. This patent has been published, and from there we made some polymeric composites that may have antimicrobial efficiency. So you are seeing that we have thin films of polyvinylidene with carbon dust of different colors, where they are transparent, but they also absorb the light below 400, which is the light that we call UV light, which is not, which is dangerous for skin and so on. So we have found that these polymers has some biofilm inhibition, and they have radical scavenging, which means that they are antioxidant. They are forming antioxidants. So they are metachellating, and they cleavage DNA of the bacteria, so they are antimicrobial by this way. So we can now we are trying to find out that if we can use them for food packaging or UV protection on not only the industrial materials but also for the skin care. So you see that we came from the antimicrobial properties and we came to the use of them in the industry for food packaging. So I hope I can give you some examples of design thinking for nano design and explain how we can use the design thinking there. So thank you very much for listening to me. I would like to thank all my graduate students and my colleagues, of course, as I thanked through the articles, but without them, these studies cannot be done. So thank you very much for listening to me. I can take questions, I guess. Miss Betül.
Hocam merhaba. Değerli paylaşımlarınız için teşekkür ederiz. Soru varsa alabiliriz katılımcılarımızdan.
I have a question.
Okay, thank you very much. Yeah, I am listening.
Oh, you can hear me. I have a question regarding the biosensing and enhancing the biosensing earlier. First, I would like to thank you for the presentation. It was very informative. My question is, like, when you enhance the signal, you mentioned like it was like 11 times. Mm-hmm. And like, can you standardize, like, can you use that biosensor to get a like quantitative results signal at the end, or like does the like decrease the threshold, but like the amount of HRP you delivered in like the single detection, is it standardized? You get every time the same, or like does it vary? That will eliminate you to get a quantifiable result at the end.
Very good question, because normally when you calculate the nanoparticle size over the inner size of it, so the theoretical results showing that I had to encapsulate like 1,000 HRP inside. Okay, this was the theoretical one. But what we are seeing from the results that the HRP signal that we can enhance was only 11 times. So when you compare with this, no, the theoretical one. But it depends on the space inside, it depends on the electrostatic interaction of the enzyme with the membrane itself. Okay, the theory is not always the right one. But for that one, of course, for different kind of, we tried different kind of lipidic formulation. This was the one that encapsulates the highest one. And of course, with those liposomes, you can encapsulate same amount in each encapsulation. Okay, so it is a standardized system. So for that formulation, yes, you can have the same signal over time, because it's not from one sensor. It is almost, we have done 10 different sensors and get the standard deviation of that 10. So it is a standardized method, but if you change the liposome, if you do a new design, the results will be changed, of course. Okay, you may need maybe a higher amount of or lower amount of signal.
Okay.
Okay, so this formulation, but for this formulation, for sure.
Oh, thanks.
Thank you very much.
Başka soru var mı acaba? Have any questions? Hocam chat kısmından bir soru geldi. Hücresel çalışmalarda kullanılan nano cımbız tekniği ile ilgili çalışmanız var mıdır hocam?
Benim bir çalışmam yok Mustafa Bey, fakat konuyla ilgili çalışan aslında insanlar tanıyorum. Özellikle Max Planck'e bakabilirsiniz. Orada bu tür böyle cımbız teknikleriyle çalışan insanlar var. Bir de yine Max Planck'te Doktor Ali, soyadını unuttum. Onlar da bu tür hücre çalışmalarında, bahsettiğiniz şey muhtemelen hücrelerin operasyonu değil mi? Bu hücre üzerinde operasyon yapılması. Orada Max Planck'e bakabilirsiniz Almanya'da.
Hocam çok teşekkür ediyoruz değerli paylaşımlarınız için.
Ben de teşekkür ediyorum beni sabırla dinlediğiniz için.
Soru soran herkese çok teşekkür ediyoruz. Her çarşamba Nano Open serimiz devam edecek. Tekrar görüşmek üzere diyorum. Hocam size de çok teşekkür ediyorum tekrar.
Ben de çok teşekkür ederim bu organizasyon için. Herkese selamlar. Tekrar görüşmek dileğiyle.
Görüşmek üzere, hoşça kalın.